Hello everyone, welcome to Refactor. In this video, we'll be learning about selection sort. We'll get to know about how selection sort works, what is the time complexity, what is the space complexity, and we'll also write some code of selection sort in Java. Now let's see how selection sort works. If you've already seen the bubble sort video that I posted earlier, then this video is going to be very easy for you. If not, I'll add the link in the description. You can go ahead and watch it and then come back to the selection sort. Now, sort is pretty much similar to bubble sort. If we remember, there were 2 points that we had to take care in bubble sort. That was, with every iteration, one element which is the largest or the smallest reaches its correct position. If it's the largest, it reaches its correct position at the end of the array. And with every iteration, the length of the unsorted array decreases. So the number of comparisons that we need to do with every iteration reduces. Same logic applies here in selection sort as well. With every iteration that we do in selection sort, one element, which is the largest element, reaches its correct position, that is at the end of the array, and with every iteration, the length of the unsorted array reduces, thereby reducing the number of comparisons that we need to do with each iteration. But there is one major difference between bubble sort and selection sort, which makes selection sort a bit more optimized than bubble sort, which is, in bubble sort, with every comparison that we do in each iteration, we also need to swap the elements. In some cases we might not, but in most of the cases there is a need to swap the consecutive elements while we do the comparison. But in selection sort, the number of swaps that happen with each iteration is just one. So if we perform n iterations, at max we'll have to do n swaps. That is the difference between bubble sort and selection sort. We take a small array and we need to sort this array in ascending order. Okay, so as I said, we have to apply selection sort. In selection sort, we have to take care of two things: that with every iteration, one element reaches its correct position. So there are four variables that we need to take care of while we are executing selection sort. One, for example, would be the ith variable, which would be taking care of the number of iterations that we perform. So we'll be going from the first element to the last element in this I variable. Then the second variable would be a jth variable. So to note, you can name these variables whichever way you want, but just for simplicity and understanding, I'm naming these this way. Jth variable would be the one which would be used for the inner loop. So we'll be doing the comparison one by one with each of the elements using this jth variable. There would be a third additional variable that we need in selection sort, which is the max element. So max variable would be the variable which would be storing the maximum, the largest element in one iteration. So we'll be performing multiple iterations, and in each iteration we'll have one largest element, and at the end we would be swapping it with the last element. And how we would be swapping it with the last element? Because we would first, in order to swap that, we would be needing the index of the largest element. So we'll also keep a fourth variable, which would be a max index. So based on these four variables, we would be solving the selection sort. So let's do it in action. We start the first iteration, and in the first iteration, we put the first element in the max. So our max would be 12, and the max index would be the 0th position. So these are the position of these elements, and 12 is present at the 0th position. So I'll put 0 in the value of the max index. Now we'll start our inner loop. This is the first iteration, and we'll start our inner loop. Inner loop will start from the next element, that would be I plus 1. So if our I is equal to 0, it will start from 1. So j would be equal to 1, and we compare it with the next element. Now we'll see whether the element that is present in our max variable, it is larger than or smaller than 42, which is the next element. Now, as the name suggests, we have to find the largest element in one iteration. So as you can see, 42 is larger than 12. So we would be replacing the value of 12 with 42. And since we also need the index of this element at the end for swapping, so we would also be replacing the index, which is 1, in the max index. Right? Now, as we move to the next pointer, j becomes 2. We move to the next element, where is 62. Now, if we see, the max element is 42, which is again smaller than our new element, which is 62. Again, we'll go ahead and replace it with 62. And we'll also update the index, which would be 2. Right? So this is replaced. Now we move to the next element. So here, this is how it would be replaced. Now we move to the next element, which is 11. Again, we'll compare. Our max contains 62, 11 is smaller. So this time we do not need to replace because our max is already larger than the current element we are at. So there would be no change in max, no change in max, and no changes in max index. And we'll move to the next pointer. Now we'll move to jth position, which is the last position, last index of the array, and we'll reach to 0. 0 is again smaller than the max element, so there would be no change in the max value or the index. Now one iteration completes here. After the completion of first iteration, we see that the value of max is 62 and the index is 2. Now what we go ahead and do, we would be replacing the last element that we have with our max element, whichever that max is. So here we would make it 62 and here we will replace it with 0. So our array now becomes 12, 42, 0, 11 and 62. And now this is the unsorted part of the array and this is the sorted part. Similarly, we will be performing the next iterations. So in the next iteration, again our max would be 12 first of all, and then we'll move to the next pointer, next element. Here the element is larger than 12, which is 42. So we'll replace the max and we'll also be maintaining an index. So it was 0 earlier. Now it will become 1. Again we move to the next element. Now it's 0. 0 is smaller than 42. So this time we don't need to replace it with anything. We'll move to the next one. Now the next element is 11, which is again smaller. And we don't need to do any changes. Now we've reached the end of the unsorted array. So here we note that, as I pointed out earlier, the second thing that we need to take care is, with every iteration, the length of the unsorted array in which we need to perform the sorting reduces. So last time we did 5 comparisons, but n minus 1, actually 5 minus 1, that is 4 comparisons we did, but this time we'll only be doing 3 comparisons. So now we've reached the end of the array and we'll be swapping 42 and 11. So our array would be 12, 11, 0 and 42. Now this is the unsorted array and this is the sorted array. 42 and 62 are the sorted array. And similarly, if we go for the next two iterations, I'll quickly complete over them. In the next one, we would be replacing 12 and 0. So the array would become 0, 11, 12, 42 and 62. And we'll also be performing, although the array seems sorted, but we'll also be performing the last iteration because the program will, the logic that we had, it will do. But here we would put max as 0 first of all and then 11, and at the end it would be doing a swapping, but that would not happen. So that is how we'll be getting the final sorted array, which would be this. Now let's see what is the time complexity of selection sort. in selection sort, if the length of the array is n, then at the first time we do n iterations. And since at the end of each iteration the number of elements reduces, the number of unsorted elements reduces, so we need to do one lesser number of comparisons with each iteration. So in the first iteration we'll be doing n comparisons, and then we'll be doing n minus 1, n minus 2, and so on. So in order to calculate the time complexity, that is the computation that we are doing, and in order to calculate the overall complexity, we'll be adding all of this. And if you observe it closely, it is equal to the linear sum of n elements. And this can be broken down into a formula which is n plus 1 by 2, which approximately can be equated to O to the power O of n square, which becomes the time complexity of selection sort. And now the space complexity. So we created 4 variables in the code, and we did not create any extra array or anything. So for every iteration we are just needing 4 variables. We are just storing 4 new variables, which is a constant number, because it's not that even if we choose 1 million numbers, we have 10 trillion numbers. Extra storage that we need is just 4 variables, so which is constant, and that's why the space complexity would be O of 1. Now let's write some code. To start with, we'll put the length of the array in a variable, and then we'll be starting our first for loop. So again, to remind, the first for loop is to keep a track of how many elements have been sorted and how many less elements are to be sorted with consecutive iterations. And then there will be an inner loop for comparing the consecutive numbers. So we'll also be starting it from the first element, so it will be length. Now here, this is the inner comparison that we make. Now with every iteration the number of comparisons is reducing, so every time it's not going to be length, it would be length minus I, because in first iteration we have to compare all the elements, in the second iteration we have to count one less, and so on. So I would be the variable that is taking care of that number, so we'll include that. But before that, there were also 2 more variables that we had to take care, so which are int max, which to start with we'll keep it as the first element of the array, that is input of 0, and then we have to maintain the index of the largest element, which we call it as max index, which will be 0 every time we start a fresh iteration. Now inside the inner loop we'll do a comparison if the element at the jth position is larger than max. If it is, then we have to replace the value of max. So input of j, that is the new element, would be put into the max variable, and also the index of the value of the max index would change to j. Now this was the work of the inner loop. Every time it does the comparison between the current element and the max variable. After one iteration is complete, what we have to do is swap. Now we have to swap the largest element that we have found, which is present in the max array, with the last element of the unsorted part of the array. So what we would be doing is, now this is something tricky that you need to understand. We would be putting the element at the max index. We would be replacing the element at the max index with the element present at the last part of the unsorted array. Now how we would be getting the last index of the unsorted array? It would be length minus 1 minus I. Why we do length minus I is something understood, I think. Length, with every iteration we are reducing the number of elements, so that defines the length of the unsorted array. That is why length minus I. Minus 1 is being done because earlier when we were doing a comparison we are using lesser than length minus I, but here we have to point to the exact index, so it would be length minus 1 minus I, because our array is 0th indexed basically. And we would be putting the max element at that position. Here we would be adding max, and that's it. That is all the code that we had to write, and now just run it. So this was the unsorted array that we have, and now we have sorted it to the correct array. So that's all for today's video. So I hope you got to learn something from this video today. If you did, please let me know in the comment section below, and we'll be back with some more videos in the future. Thank you.